This is the alpha tuning curve. First we will see the Python code, then the visualization, and finally the definition. So we already have the fitted model in the pipeline. So what we are going to get is ridge CV pipeline dot named steps model. See, taking our pipeline, we have the steps, preprocessor, and the model. Where is it? It's inside. Okay, no problem. I think we can get it in ridge. We have preprocessor and model. So from that we can, from named steps we can get these two. So I'm getting it from model. So this will be my ridge CV model. Then we are going to get all the alphas. So we already have alphas there, ridge CV model dot alphas, which we have provided in the log scale. So next, the MSC path, that will be ridge CV model dot all the CV values. Okay, and we are going to get the mean around the axis equal to 0. So each column corresponds to an alpha's CV error for every sample. So to get 1 MSE per alpha, we are going to average over the samples, that is axis equal to 0 and not along the axis equal to 1. So these are our prerequisites. Then we are going to plot it as usual. plt.figure. I'll give the fixed size is equal to 8,6. Then we are going to plot the alphas. So all alphas, then the MSC path. Okay, so this will be the X, this will be the Y, and to mark it we'll use O. Color will be teal. So next we are also going to show the best alpha line. So that will be plt dot AXV line, that is going to be a vertical line. For that I am taking the model's best alpha, that is dot alpha underscore, right? Then for this line style will be dash dash, then color to visible, for visibility I'm giving red. Then for the label it is, this is the best alpha, right? So for that so I'll format it. Okay, let's take 3. Close the brackets. Next, so we need to scale the x-axis like in log. So plt dot x scale of log, because we have given the range of alpha in log, right, in the log space. That is this. We have given our alphas in the log space, so that is why we are going to scale the x with log. Next comes the labeling part. So plt dot x label, or x label signifies the regularization strength, right? So that is our alpha. Then for this font size can be 12. Then comes the y label, that will be mean CV MSE. So we have got the mean of CV for this MSE, right? So that path, it will be font size 12. Then our title, which is ridge CV alpha tuning curve. So for this font size a little bigger, 14. Then finally plt legend, plt type layout to ensure everything is intact. Okay, underscore. Then plt dot show off. Let's see any error. Now we have got the alpha tuning curve here, right? The best alpha is 12.068. The x-axis is the regularization strength. The y-axis is the mean CV MSE. So we have also marked the vertical line of best alpha. Let's analyze this curve. So we can see the logarithmic scale here, that is from 10 power minus 3 to 10 power 2. So we can see one similar kind of curve here, that is from 10 power minus 3 to 10 power 0, let's take. So here the curve is flat. So this means that even small amounts of regularization has no effect on our model. It behaved like a linear regression, that is the ordinary least squares, as we have already discussed. So from 10 to 10 power 1, 10 power 0 to 10 power 1, our mean CV MSE actually dropped a bit. So here it went to find its absolute minimum point right around the best alpha, 12.068. So like if we add a moderate penalty successfully, this will filter out some data noise so that our generalization slightly gets improved. Then starting from 10 power 1 to 10 power 2, we can see a sharp upward curve, right? So the penalty is becoming too heavy, and this is forcing the coefficients aggressively towards 0, right? So this will be like underfitting our data. Instead of using log space, we can also try with linear space, that is LIN space. So because we had more points in this flat section, so I think because of log space, because we had only 50 points, right? So almost more than half of the points are in the flat zone. So using log space, it will set us with a large number of numbers, so that we get more number of test points without much gap here. So I think instead of approximating the best alpha value, we can get some precisely correct alpha value when we are using lin space instead of the log space. So let's see what this alpha tuning curve really is. So we are having the problem of bias and variance, right? So there is a bias variance trade-off we need to do. So this alpha tuning curve, what it does is, this is going to be a diagnostic plot, because we can diagnose like where the alpha is, where the value is, likewise, right? So this is used in regularized regression, that is we will be seeing the same curve for the lasso, but we can compare the performances later. So this will visually solve the bias variance trade-off. This is because this is going to plot the regularization strength, that is the alpha on the x-axis, against the metric, that is our mean squared error, that is cross validated. So this will be on the y-axis. So this exact plot is used to identify the optimal hyperparameter, that is the alpha, that minimizes the generalization error on the unseen data. So before plotting that, we need features that are scaled. So scaling should be done. Then we have got a set of alphas, right? So we have used log space. We can also use lin space. So this log space is to find the right order of magnitude, and it is followed by the lin space. So this will give us the precise value. Then we have to do the cross validation, because we cannot use raw training error, as it's always increases when alpha increases. So we must use a k-fold cross validation strategy to get this unbiased estimate for the performance. So then comes evaluation metric. We are going to use the mean squared error. So this is going to track the average of this MSE value across every tested alpha value. Next is a cross validation error curve for our GridCV. So let's code. First we have our GridCV pipeline. From that named steps, we will take model. This will give us the GridCV model. We have already done it. then all alphas we will get it from this model dot alphas. Then we are going to get the CV values. So here we got the MSE path for the alpha tuning curve, and for cross validation error curve we are going to get the CV values, that is from the CV value. So here we have used the mean of the CV values, and here we are going to just use the CV values. So from here we will calculate two things. One is the mean MSE, then the standard deviation STD MSE. Okay, so this is going to be from the CV values. So for that mean I will take NP dot mean of the CV values, comma axis equal to 0. Then for standard deviation NP dot STD axis equal to 0. Then we are going to calculate two things. One is the best alpha and the other is the best index, right? Which will be best alpha ridge CV model dot alpha underscore, then best index, that is the mean argument of the mean, right? So np dot argmin of mean MSE. So this is the best alpha, and where the best, in which id the best alpha is there. Then we will plot it plt dot figure of fig size equal to 8 comma 5. So now we are going to get the individual CV error curves for all the alphas, right? So plt dot plot of all alphas comma CV values. We are not going to plot all the alphas, sorry, all the CV errors. We are going to just visualize some 50. So color will be orange. Then we are going to get the mean CV error curve. First is the individual CV error curve. So that is this thing. Then we are going to get the mean CV error, right? So for that we will be using the mean MSE. So plt dot plot of all alphas comma here mean MSE, comma color will be teal, let's say 3 thicker. Next this will be mean CV error. Now we are going for the stability bank, right? We need plus or minus one standard deviation, that is going to be a shaded portion here. So this is, I'm going to name it as stability bank, right? So plus or minus one standard deviation. So plt dot fill between. So I'm going to make it as a shaded portion, that is why fill between. I'm going to take all the alphas, then on the left it will be mean MSE minus STD MSE, on the right mean MSE plus STD MSE. So this, the color will be teal, alpha will be 0.2, label will be plus or minus 1 standard deviation. Next, after filling that with the color of teal, I'll be drawing the best alpha line. That will be plt.ax vertical line with best alpha, comma, the line style will be the same, right? Next, we are going to do a scatter plot here. So the scatter plot is going to be between the around the best alpha. Like we'll be picking out the index, like not around the like not around the all alphas. You're going to get the best alpha, and we are going to point the what to say, the best alpha, the index where that best alpha occurred. Okay, so that will be plt dot skate. I'm going to plot it. So for the best alpha, from the mean MSC, I'm going to take the best index value. From the mean MSC, I'm going to take the best index value. Then the point will be black in color. Label will be this is going to be our optimal point. So now our alpha scale is log plt.x label. So regularization strength, I'm going to copy all this. Okay, alpha, this is going to be our not our mean, this is going to be cross validation MSC. This is not the alpha tuning curve, this is the GridSearchCV cross validation error curve, right? Let's see if there is any error. Okay, we have got the plot. Our x-axis is the regularization strength, and our y-axis is the CV of cross-validation mean squared error. Then we have few orange lines in between. So this is the MSE for each CV fold in the given alpha. Then a teal line, right? So this is going to be the mean of all the other folds. So the teal line is the mean MSE of all alphas. Sorry, here mean MSE of all alphas. Then we have got the shaded region, right? So this shaded region is like plus or minus 1 standard deviation. This will be giving the variability in the error across our folds. So this line is our best alpha. This is where the mean CV error reaches the minimum, that is our this teal line, right? So this is the point where it reaches its minimum. So then the black dot is the like optimal point, so that is visually like pleasing to see. Next we did the fill between, right? So this is going to the shaded region. This creates a shaded confidence band like around the mean CV error curve. This will create a very confidence band around the CV errors. So next, this band, what it does, this represents the uncertainty or the variability in the MSE across the folds. So we have two types. One is a narrow kind of thing, and the other one is the wide band. If it is narrow enough, the model performance is consistent and consistent across the CV splits, which tells us the model is stable. And the wide band tells us that the higher the variance between the folds, that is a model is less stable. So this is going to be the stability indicator. Unfortunately, our see this teal line, this is almost completely fat across 10 to the power of 3 to 10 to the power of 2 itself. So this is completely flat. So that means our regularization is not doing anything like changing our overall model performance, anything that kind. So okay, this is stuck around 0.15 itself. Even though we have got 12.068 as the optimal point, but we don't have any value here. Okay. The model is highly sensitive, so any kind of severe outliers like this will completely dominate our mean squared error. Like when a fold contains that outlier, error spikes to like more than 0.7, and when it doesn't, it drops to 0.0. So likewise, a few massive outlier data points would have been there. Then the low sample size or any like our data set is very small. In that case also there is a highly instability, right? So we can also tell that our features don't have any strong linear relationship between like along with the target variable. So if there is no if there is no feature no predictive power for the features, then regularization can't fix anything. So the rich CV error, like this cross validation error curve has like it told us that our model is a complete failure. By using this rich CV, we are like working with leave one out CV, right? So, but our weather data is a time series data. So we have already seen that while splitting the train test split itself. But by using rich CV, this will only work out with the leave one out CV, right? That will be shuffling. So we can shift to grid search CV combined with the time series split in order to calculate this error properly. So this is one thing. So that is why our model, like our graph, is very much confused. So weather data is highly sequential and is dependent on time. So by using this default cross validation, so we are shuffling the rows. So this will be like leaking the data and temporal volatility. So this is going to be like this curve. This error is one of the best examples for data leakage and how the model is like varying here and there, and very clumsy curve. And this particular model rich CV for weather forecasting is very much useful. It's very much not useful without time series and time series split and our grid search CV. So we can come again and try with our time series split along with the grid search CV. So I think we can do it with like first splitting the data set in 5 splits and recreating our pipeline, and for that we can send that time series splits as cross validation, and we can create the grid inside for the grid search CV where the estimator will be the rich. So in that way we will build the pipeline with the grid search CV and perform the model pipe, perform the training. Then we will get the CV results and alphas and calculate all the other three things, that is B, mean MSE, standard MSE, best alpha. Then we will replot it. So I think that is the best way to do. So let's see in the next video. So without doing appropriate steps for the appropriate business context, we will be getting the false error. So that is why business impact and business context is very much important while doing the graph, doing the pre-processing, everything. So it's a new learning.